Hello everyone, welcome to the manufacturing processes class. In this video, we're gonna discuss we're gonna continue the metal casting process. In the previous meeting, we already discussed the sand mold design and we give examples. Here we're gonna move to another topic which is related also to the metal casting process and especially the sand casting, which is related to the gearing system and the buoyancy force. Also, we're gonna discuss through this video the riser design. So we already discussed in the class the gearing system, and we gave a very quick hint about the buoyancy force, but we're gonna go over these two terms with more detail. The gearing system, as we discussed before, that this is the set of passages or channels that would be used for transferring the molten metal into the mold cavity. Like in order to pour the molten metal into the mold cavity, it should be poured to allow for the steady state laminar flow of the molten metal through the different channels to be filling into the mold cavity. And to do so, we have to set up, while we're already doing design for the sand, for the mold, sand mold, we have to set up these gearing systems or this gearing system and these different elements that we already consider in the sand mold design. But we're gonna go over the function of every one of these elements with more detail. I have discussed these functions or the objective of all of these elements before, very quick before, but here we're gonna give more detail over these elements. So generally, the gearing system is all the passages through which the molten metal enter the mold cavity. How we allow or transfer the molten metal to fill into the mold cavity, this should be done through the gearing system. And this gearing system, it has different elements. So these are the elements of the gearing system. This include the boring basin or boring cup, which is the first thing that we're gonna see from the top of the mold of the sand mold. And basically we're gonna pour the molten metal through the boring cup, which is gonna fill the boring cup. Then it's gonna be smoothly and easily flow down to the down sprue or the sprue. So the second element that comes directly next to the boring cup is the down sprue. Then after the down sprue, there should be sprue well. And we said that this sprue is going to work like a reservoir that is going to collect the molten metal to allow also for a laminar flow of the molten metal through the runners. So the runner is the other element that exists for the gearing system. Also, the next element is the runner extension. And we're going to discuss the function of this runner extension, that most of the slags will be collected in the runner extension. Then we do have the gates or the in gates, which are the openings directly that it should be filling into the mold cavity. Assume that we do have something like a mold cavity located within this area. So these are the gates that will be automatically filling into the mold cavity. So these are, again, the different elements of the gearing system. And we're going to go over the function of each one of these elements with more details. But before we do so, let us know the function of the gearing system at all. What is the function, the general common function of the gearing system with all of these elements together, why we are using this gearing system. So the gearing system should be designed to achieve some of the requirements, and this would be considered, like as I mentioned, the functions of the gearing system or the requirements that should be considered while we're already doing design of the gearing system. First of all, the gearing system should allow for low flow velocity of molten metal. It means that, or in other words, to allow for laminar flow of molten metal to fill into the mold cavity, to allow for the easy flow of the molten metal. So we have to design the gearing system with this essential requirement. We have to avoid any turbulent flow. Turbulent flow, as you know from the fluid mechanics class, that turbulent flow, it have like vortex or vortices already forming. It means that the liquid or the molten metal is gonna start to twist or rotate, and this is gonna give it's gonna trap some air and collect this air and through this air inside to fill into the mold cavity. And one of the essential requirements of the sand mold design or the metal casting process in general, that we have to avoid the hot air or the air to be trapped inside the mold cavity. So we have to find any way to get rid of the air from inside the mold cavity to be outside the mold cavity. And so that's why one of the things that we have to design this gearing system to allow for the laminar flow, because as I mentioned, the turbulent flow will bring more air into the mold cavity, and this is going to be a serious problem. Another requirement, that complete filling of the mold cavity. Like for example, if we messed up with the design, if we had a bad design of the gearing system or a wrong design of the gearing system, probably the molten metal is going to cool down very quick, and it won't gonna be able to fill and fluid to fill into the mold cavity. So it means that we're gonna end up with an incomplete product or casting product or incomplete filling of the mold cavity, and this is also one of the serious defects of the sand mold design or the metal casting process. Also, the gearing system, it should prevent the aspiration. As we discussed before in the class, the aspiration, it is one of the serious problems that would exist, or it is a phenomenon like breathing air. Aspiration, it means that we're already breathing air to fill into the mold cavity. And this would happen in case that we do have a straight down sprue, as we're gonna discuss for the down sprue right now. But in generally, one of the essential requirements for the gearing system, that it should prevent the aspiration. Also, it should prevent formation of oxides. Oxide basically, since we are talking about metals, and this is also, we had a discussion about this thing in the material science class. Since we are talking about metals, metals are very good material that can be easily interact with the oxygen that already found in air in the conventional environment. So metal and oxygen generally, they are good material that can have put into chemical interaction easily without any other agent that would enhance this chemical interaction between the metal material or the oxygen that already exists in the environment. So oxides is basically like, for example, if we have Fe, which is just metal, and we added some oxygen, so this is going to give us the FeO2O, which is the conventional rust. So this is one of the oxides that would exist. So generally, and since the metal is very hot, so it's easy for the metal to be in chemical interaction with the oxygen in the environment. So we have to design the gearing system to prevent any kind of deformation or this chemical interaction or exposing the metal somehow to the environment. So we're gonna prevent the formation of the oxides. It means that the gearing system should prevent the exposure of the metal or the molten metal to the oxygen in the environment, the conventional environment. So we're gonna prevent the formation of oxide. This is one of the essential requirements of the gearing system. Also, the gearing system should be designed to prevent the entry of slags or jaws or dirts or impurities inside the mold cavities. We would like to allow only for the pure metal to be filling into the mold cavity. So any slag, any jaws, any dirts, they are not allowed to come in or to fill into the mold cavity. So we have to take precautions while we're already filling or pouring the molten metal during through the gearing system, and we have to put some obstacles in front of the slag or the jaws and dirts to fill or to fill into the mold cavity. This should be done while we already do design for the gearing system. Also, assist directional solidification. What does it mean, directional solidification? And this directional solidification is a big deal, especially in case that we do have huge castings, big casting. As we mentioned before, one of the properties of the sand casting process, especially if we're considering the sand casting, that we can make products that weigh up to 200 tons, which should be a huge product, right? So directional solidification, it means that we can control somehow which part or piece of the molten metal that should be solidified first, which should be solidified next. This is directional solidification. And this basically depends on the direction, the size of the casting. And this directional or solidification issue is a big deal, as I mentioned, in case that would have huge castings, because the casting itself, what we would like to achieve while we already during the solidification process of the casting, that all the metal should be solidified at once at the same time. It means that we have to the same rate of solidification through all the material to have a consistent material. As you remember from the even we discussed here in the manufacturing class, that we do have the heat treatment processes. Heat treatment, it means that you're gonna heat the material into a certain temperature and you're gonna allow for the cooling of the material at a certain rate. So the rate of cooling down the material, it is a big deal. The rate of solidifying the metal, it is a big deal. It will result in some, if we change the rate of solidification of the material, we're gonna end up with different mechanical properties. So in order to end up with homogeneous casting, it means that, what does it mean homogeneous? It means that the casting, it should have all the, at any point, it should have the same mechanical properties. In order to do so, we have to achieve that the rate of solidification all over the casting, it should be the same. Like at any point belong to the casting, all the molten metal of the casting, it should be solidified at the same rate. To achieve this, we would require to consider the directional solidification, because the sand, it is a shell. What does it mean, shell? Shell, it means something that is gonna be used for cooling down or solidifying the molten metal, right? Decreasing the temperature of the molten metal. As the molten metal exposed or touches the sand, more surface of the sand, it means that it's going to solidify faster. It's gonna cool down faster, because the sand, it is cold, it is shell. It's gonna use for cooling down the molten metal or decreasing the temperature of the molten metal. So in case that we do have some parts of the molten metal that are exposed to a bigger surface area of the sand than other parts, it means that this part will solidify faster than the other one. So we have to do design of the gearing system and put the gearing system into somewhere to allow for the same rate of solidification everywhere through the gearing system. Make sense? Also, it should be practical and economical. It means that we have to make design of the gearing system to be easily designed, practical thing, that we shouldn't come up with a gearing system that cannot be applied, right? So these are some essential requirements of that, and some essential aspects that should be considered when we do design for the gearing system. Automatically, we did this, we consider these things in our design of the gearing system in the sand mold design problem. When we discussed the sand mold design problem, we did some calculation, and even we use some formulas. These formulas and calculation basically, or this procedure that we explain, automatically consider these requirements into account. So that's why these requirements already considered while we already do design for the sand mold. Okay, but generally these are the essential requirements of the gearing system that should be considered. Or in other words, these are the general functions of the gearing system, that it should prevent aspiration, prevent formation of oxides, prevents entry of slag or dross into the mold cavity, in addition to allow for some directional solidification as we just mentioned. All right. So now what we're gonna do, we're gonna go over each one of these elements one by one and see the function of all of these elements, starting with the boring cup, which is the thing that already located on the top here. We said that the boring cup, this is the first thing. This is where we're gonna put the molten metal or pour the molten metal into the boring cup first. Then from the boring cup the metal is gonna flow through the other elements of the gearing system. So the boring cup is important to assure steady flow of molten metal into the down sprue. If we try directly, assume that you do have a down sprue in this way, as we discussed before, and if we try to pour the molten metal directly into the down sprue, it will not go steadily. It means that it's gonna have a vortex flow or turbulent flow, so it's gonna trap more air and bring more air to fill into the mold cavity. This is the down sprue. But the other option actually to get rid of this problem is to build a boring cup here and then pour the molten metal not directly into the down sprue. No, we're gonna bore it into the mold cavity, into the boring cup. Then the molten metal will be smoothly and easily flow to fill into the down sprue to fill into the mold cavity. So that's why it is important to assure the steady flow of molten metal. Also, molten metal is poured into the boring basin or the boring cup, which acts as a reservoir from which the molten metal smoothly enter the down sprue, as we mentioned, that we collect, even we bore here, then the molten metal is gonna be collected somehow and smoothly and easily start to flow to fill into the mold cavity. These are the standard sizes and depths of the boring cup, that it would be 50 millimeter, 100 millimeter, 150, 200, and 250 millimeters. As if you remember in the sand mold design, the last step, we said that in case that the boring cup depth is not given, consider this value as 50 millimeter. This is just an assumption, but you can consider any other values. It's up to you. But for most of the casting that we considered in the problem, it means that the small casting 50 millimeter is a good size for the boring cup, but it would increase depending on the size as we increase the size of the casting. Also, the boring cup, it should be used, and this is one of the essential requirements also. So the boring cup, it has two essential functions. First of all, to allow for the steady flow of the molten metal. As I mentioned, if we try to bore the molten metal directly to the down sprue, this is going to give a turbulent flow. So we would like to have a laminar flow, steady state flow of the molten metal to fill into the mold cavity. This won't going to achieve unless we bore the molten metal into the boring cup first. Then from the boring cup, it's going to steadily flow to fill into the down sprue. Also, another function that we can even start preventing the slag, because as we mentioned that one of the essential requirements of the getting system is to prevent the slag to fill into the mold cavity. So to avoid or to prevent or overcome the slag from being to fill into the mold cavity, we can do so from using the boring cup. We can use skimmers or skim cores, strainers or dams. Like for example, this representation, these are different boring cups. All of these parts, this is a boring cup. This is the boring cup. And as you can see, this is the cavity of the boring cup. This thing, this area, what is already exists here, should be the cavity of the boring cup. So when we bore the molten metal, we're gonna bore the molten metal into this area. So the molten metal will keep filling this area. Then it will be steadily and easily and smoothly flow between this skim core. So this is one of the options. The function of this skim core is to prevent the slag. So what happened basically, in many of the cases, the slag, it has a lower density than the pure metal itself. The pure metal is heavier than the slag or the dirts. So what happened basically, that the dirts already start to float over the surface of the pure metal. What already on the top here is just slag. And the pure metal is going to be located down here, which is going to be easily flow to fill into. This is the down sprue. This should be the sprue. So it's going to fill into the sprue, moving to the mold cavity after that. So this is the function of the skim. So the skim core, it holds back the slag or dirts which floats on the top and allow only clean metal or pure metal underneath it into the down sprue. Make sense? This is one of the options. The option is just to use strainers. A strainer like this strainer that is used in the water sink in your home, right? So strainers, you're gonna put, this is the boring cup and you're gonna bore the molten metal. So molten metal is already filling everywhere. When the metal try to come into the mold, this should be the down sprue, this should be the sprue. So what happened here is the molten metal is gonna go through these openings, and the thing that is gonna pass through the openings of the strainer is gonna be only the pure metal, and all the dirts will be collected here. Then after a while we can remove this strainer to clean it and put it back again and bore more and so on. So this is how it works, but it is not practical in all the cases. But this is one of the ways or methods of avoiding slag or dirts into the mold cavity using the boring cup. Make sense? So strainers restricts the flow of slag into the sprue, it controls the flow rate into the down sprue as well. It has two main functions. We can use it also to control the flow rate of the molten metal into the boring into the down sprue. Another option, which is more practical and it is more easy to use, is using dams. Dam, it would be anything. Like, for example, in some cases, we would put a piece of wood or a piece of metal in front of the bore metal at a level here. Like, this is that any dam, anything that we're gonna put by hand, it shouldn't be set up over the boring cup itself. It means that this is the boring cup and this should be the down sprue, and we're gonna bore the bolted metal here. It's gonna filling into this area, and we're just gonna put anything that is gonna work as a dam. So what is on the top? All of these are the dirts and slag already located over the top because of their light density or small density. But the pure metal is going to be located here. This is only the pure metal, right? So the pure metal is the thing that is going to be allowed into the down sprue, and all of this area is going to be all of it is just pure metal. Pure metal. So all of these are different methods and approaches of preventing the slag to fall into the mold cavity while using the boring cup by using skim cores, strainers, or dams over the boring cup. Make sense? The second element that we're going to consider here is the down sprue. The down sprue also, this is the element which comes directly after the boring cup. It is the vertical passage that connects the boring basin or the boring cup to the sprue base. The sprue base, this is commonly known as the sprue well. Okay, if we're gonna go back again to the gearing system, this is the down sprue which connects the boring cup to the sprue well or the sprue base. This is the sprue well or the sprue base. Make sense? So it comes between the boring cup and the sprue well and the runner as well, because what comes after the sprue well and the runner. So this is the channel that connects somehow it connects mainly the boring cup to the runner directly. What is the runner? The runner is like a passage of the molten metal, but is perpendicular to the down sprue. Like we're already boring up vertically, then we're gonna switch the direction of the flow of the molten metal to be horizontal, right? Because if you're gonna go to here in the boring into the gearing system, we are boring vertically through the down sprue, then the direction of the molten metal will be changing to be horizontal in this way, right? So to have this change, abrupt change in the flow, we have to use here the sprue well or the sprue base, as we are going to discuss the function of this one. But there is an important function of the down sprue, okay? The down sprue, the cross section of the down sprue is usually round, but in some cases it would be square or rectangular. But the common thing there is round. And there are some essential requirements of these down sprue that they should be short and tapered. So these are two things. First, they should be short. Second, they should be tapered. Why? This to minimize the aspiration. What is aspiration and turbulence, which are the turbulent flow? As we mentioned, for example, to understand the aspiration, let us compare the straight sprue to the tapered sprue. The straight sprue, if even you can experience, you already experienced the thing while you try to open the water vent at home. If you open water vent, the water will be, because of the surface tension, will be somehow at the tip of the vent. It will be very, very thick, right? This is the water from here will be very thick. Then because of the surface tension, the water particle will start to merge together, and you're gonna end up with a very thin like diameter of the water itself. This is gonna leave some areas here surrounding or around this water or this liquid, okay, in general. This area, this empty area, definitely it will have some air, and this air will be trapped and collected to fill into the mold cavity. And as we discussed before, air inside the mold cavity is a serious problem. It's gonna result in some defects in the casting. One of the essential defect is the porosity. Like these airs will be trapped inside the mold cavity. So this is one of the serious problem of the straight sprue. So it is better to have it like tapered. If it is tapered, these cavities will not be exist anymore. It means that we are not allowing for any air to be breathed in to fill into the mold cavity. So aspiration simply, it is a problem. Aspiration, it is a problem, and we have to make the down sprue tapered to avoid this problem. What is the aspiration? It is breathing the air to fill into the mold cavity, or trapping the air to fill into the mold, or bringing more air to fill into the mold cavity. This is all means aspiration, right? Turbulent flow also another thing, because if it is not tapered, we are allowing for this water particle to easily rotate, right? And the twisting or the vortex rotation of or movement or flow of this liquid, this means that we do have a turbulent flow, and this is going to bring more air by default to fill into the mold cavity. So these are some essential requirements of the down sprue, that it should be short and tapered to avoid aspiration and the turbulent flow while we're already boring into the mold cavity. So again, aspiration is the process that involves breathing atmospheric air into the low pressure area around the molten metal when flow in the straight sprue. This problem shows up in case that we are using straight flow sprue. That's why it is advised to use tapered one. Aspiration is avoided by means of short and tapered down sprue. These are two essential requirements. The long one and tapered would result in some aspiration, but the aspiration, it will be completely eliminated as long as we are using short and tapered down sprues, right? The next element, what comes after the down sprue, just keep the gearing system in your head, right? We do have the boring cup, then the down sprue, then the sprue well or the sprue base. So the sprue base or sprue well, it reduces the velocity of the molten metal before it enters the runner. As I mentioned that we already have a molten metal that flew vertically in the vertical direction through the down sprue. Now we would like to switch the direction of this flow to be horizontal. So if we try to directly switch the direction of the vertical flow to be horizontal, definitely we are losing the concept of the laminar flow. There is no laminar flow anymore. The flow will be turbulent flow automatically if we did it directly. So that's why we have to give ability for the metal to be collected first and to easily and smoothly flow, to keep the laminar flow requirement as requirement to avoid breathing air into the mold cavity as we discussed before. So how it works, that we gonna have the molten metal, and this big area here, it is the boring basin or the boring cup. The sprue base or the sprue well. Like the molten metal will be collected here first, then it's gonna steadily flow to fill into the runner. This extension, these parts, this part here, this part here, these two parts are the runner. This is the runner, and there should be another runner. It means that some of the molten metal will move left and the other will move right. Okay, that comes, this is the down sprue. This should be the down sprue. So the metal that comes through the down sprue will be collected in the sprue well first. Then it will be distributed over two runners or more. We can set up like 5 or 6 or 4 runners. It's up to us. It depends on the design. We didn't discuss, or we didn't consider cases that require multiple runners, or we didn't discuss in the design process of the sand mold multiple runners or multiple gates, but this practically would be used. Like we would use multiple runners to feed different mold cavities. Even we discussed this thing very quick in the class before, right? So the function of the boring cup is just to allow for the collection. This reduction this leads to a reduction in the momentum of the molten metal is needed to reduce the mold erosion. Mold erosion also to trap more air, as we discussed, to fill into the mold cavity, because as I mentioned, it is hard if you try to switch the direction of the flow of the metal directly or very quick. This is going to result in high momentum of the molten metal and is going to result in some turbulent flow. In addition, it's going to result in some erosion. Erosion, it means that pieces of or some parts of the sand of the mold will be broken down and it will be trapped and move and flow with the molten metal to fill into the mold cavity, right? So that's why we have to use the boring well to allow or to prevent or avoid this problem. And these are the standards of the sprue well diameter in comparison to the runner width. In case that the width, as if you remember in the mold design, we said that the runner typically takes like a trapezoidal shape, right? So you can pick the biggest width, for example, in case that we're already using just one runner, and the down sprue base, it should be double the width of the down sprue runner to allow for the laminar flow of the molten metal. In case that we do have two runners, so we have to use 2.5 times the runner width, which it should be the bigger width of the runner in this case. But this part, I didn't ask you in the design process to do the calculation for the down sprue diameter, but this is what we already mentioned here, that this is typically the standard values for the down sprue, the sprue well or the sprue base diameter in comparison to the runner widths. In case that we are using a trapezoidal runner, you're gonna pick the largest width, which should be on the bottom in this case, for one runner or two runners as we just mentioned. Okay, the element what comes next, what comes after the sprue well runner, it would be one runner or more as we just discussed here, right? So the runner, it is located in a horizontal plane and connects the sprue to the end gate. It connects the sprue because what comes after the sprue, it should be the sprue well, then the metal from the sprue well will be distributed to the runner, and the runner is gonna start to give the molten metal through the gates. The runners are made trapezoidal, as we mentioned, cross section in many of the cases to trap slag and avoid aspiration. So for two main reasons: first, to trap slag and avoid aspiration. This is the second requirement. Because, for example, if we consider a trapezoidal runner like this one, so as we discussed, while we already putting some obstacles for the slag and the dirt to fill into the mold cavity or to go through the down sprue, probably for some reason and definitely there should be some slag that will be anyway come through the down sprue, right? So I have to have a backup kind of for these extra slag that escape from the trap that already build up for the through the pudding cup. But anyway, if we still have some slag, this slag also should be prevented. We can do so through the runner, so that's why it is better to have it like trapezoidal for two reasons. The first one is that the runner, first of all, it should be completely filled with metal, molten metal with liquid, but this liquid, it will include the impurities or the slag, which should be located over the top here because of their low density, and the pure metal is gonna be just located blue. So what's gonna be here, this is just the pure metal. Make sense? So this is just, and consider that this is the extension of the runner, that it already the molten metal go in this direction, right? So the molten metal, the pure one, is gonna keep going down at a low level, and the slag is gonna be trapped. So that's why it is trapezoidal, and trapped and collected somehow on the top of the runner. This is one of the functions of the runner, and that's why it is long somehow. In addition, it avoids aspiration. That's why it is tapered. That's why it is trapezoidal, to the same issue, the same concept of the down sprue, why it is tapered, for the same reason we are using runners here, tapered, to avoid aspiration, right? What comes after the aspiration is a runner extension. So what happened to this slag? This slag is gonna keep moving. Then what we do, because the runner, there should be runner, and over the runner we're gonna open the like a small opening here. This opening, it should be the in gate or the gate. So what happened here? Basically, we open a small opening here over the runner through the sand, where the molten metal, it should be somehow very close to the base. Why the base? Because the molten metal is already located down. So the thing that is gonna go through the in gate, and the in gate, this is the gate to the molten to the mold cavity. This is the opening directly to the mold cavity. So the molten metal will be the one who is gonna be filling. Here we're gonna allow only for the pure metal to fill into the mold cavity, and the slug will be keep pushed through the runner till the runner extension. If you will go back here to the getting system, we do have, this is the runner, all of this is the runner. And these two parts are the openings, which are the gates to the mold cavity, right? This is the runner extension that I'm talking about. This runner extension is gonna be used as a collector for the slag, because there is a slag, and I didn't allow for this slag to be entered to the mold cavity. So, but anyway, this slag, if I couldn't find any way to collect this slag or push this slag from the action or from the from filling into the cavity, it will be trapped and collected, and it will be accumulated and increasing, and definitely some of the slag will be filling into the mold cavity. So to get rid of the slag, it will be keep pushed as long as we feed more or more molten metal. So it's gonna be keep pushed till it's gonna be trapped and fill into the runner extension, and this is the function of the runner extension. Make sense? So this is for the runner and the runner extension. So runner extension used to prevent slag and sand particles from entering the mold cavity. It provides the suitable time for lower density particle to float, which are like the slag and other things and dirts, to float to the top of the molten metal and to be trapped and collected in the runner extension. Okay, to explain this point more, I'm just gonna use here, let me explain it more how it works. Assume that this is a runner. Again, the runner is just kind of trapezoidal shape, right? Assume this runner like this is like the best way in your college, for example, to the classrooms, or kind of. And there should be this runner, it should be filled with molten metal. All of this is just molten metal. Molten metal already exists everywhere in this case, right? And there should be the runner is already filled by, already we do have like a down sprue here, and the molten metal has been switched direction through this sprue well to fill into the runner, and the runner is completely filled. So what we basically do, we just do a little bit opening here and another opening, for example, another opening. All of these openings are the gates, or we can call them as in gates, as we agreed, right? So all of these gates, since they should be located somehow very close to the base, this distance should be very small, or even it should be opened over the base directly. So we are allowing here for only the pure metal to fill into the mold cavity, and definitely this, all of this area, it will be the mold cavity, right? So we're already filling into the mold cavity, we already pouring molten metal into the pure metal into the mold. This should be the mold cavity. Make sense? And how about the slag? The slag is gonna be trapped on the top, and all of this layer, assume that all of this layer on the top here is just slag particles or dirts, and these dirts will be kept pushed and flew till it will be trapped and collected in the runner extension at the end. So there should be here a runner extension that is gonna be working, is gonna be considered like a collector of these dirts, right, inside the mold cavity. Make sense? What comes after the gates, as I mentioned, after the runner, there should be the gates or the in gates, and these are the openings directly to the mold cavity. And the diameter of the gate, it should be with a specific value in comparison to the size or the dimensions of the runner, as we did in the design of the sand mold. We consider that we do have multiple gearing systems, and this is what we're gonna discuss here. Gates are the openings through which the molten metal enter the mold cavity directly. It transfers the molten metal from the runner to the mold cavity. This is the opening directly to the mold cavity from the runner. In pressurized system, and we said that if you remember that we do have pressurized system and non-pressurized system. In pressurized system, ingates are the main controlling area which control the metal flow into the mold cavity so that the mold cavity is filled within the calculated boring time or filling time. There is filling time or boring time. This is the time, as we discussed, this is the time needed to completely fill the molten metal, the cavity with the molten metal. And this boring time, as we discussed in the sand mold design, like for the case, the boring time, if you remember, for the case of steel casting, it was S times the square root of G, where G, this is the gross weight or gross mass of the casting, and C, this is constant that depend on the material type of the casting itself. For a cast iron, we'd have another formula, but anyway, the boring time, it is a specific time that depend on the material type, that depend on the size of the casting. And as we discussed, the boring time, it shouldn't be too short and it shouldn't be too long, because too long, it means that the molten metal won't gonna be able to fill into the or completely fill the mold cavity, so we're going to end up with incomplete casting due to incomplete filling of the mold cavity. Or if it is short, so it means that we're already boring very fast and we are allowing for the for trapping more air and lots of other problem, as we discussed before for during the sand mold design. So that's why the boring time it should be optimum. It shouldn't be too short, it shouldn't be too long. It should be consistent with the design or the casting that we're already considering. So in the pressurized gearing system, the end gate area is the controlling area. It's the thing that control how fast the molten metal will be filling into the mold cavity. So it is important. All right. And generally, as we discussed in the sand mold design, we do have pressurized system that molten metal flow is restricted at the end gate. Like the area of the runner, the area of the sprue and the area of the runner, both are bigger than the area of the end gate. So what does it mean? It means that it works like you're already using, this is the runner in this case, and you do have a very small opening here. So for the molten metal to fill into the mold cavity, the molten metal will be pushed. It is pressurized. Okay, it is fluids under pressure to fill into the mold cavity. This is in the pressurized system, and the area of the end gate, it should be smaller than the area of the runner or the down sprue. It is used basically for ferrous mirror and copper alloys. In case that we do have ferrous metal like steel castings, for example, cast iron steels, it is preferred to use the pressurized system. For copper alloys, also it is preferred to use pressurized system, but non-pressurized are used for any for other non-ferrous metals in general. Also, for the non-pressurized system, it reduces the melt velocity to allow slag to float to enter the runner extension. This is gonna allow for the slag, because one of the serious problem of this thing that it's gonna, because of the small opening and the lots of pushing of the molten metal here, right? You're gonna find that the metal, it will be somehow attracted to flow through this opening, this small opening. This attraction of the molten metal will, in some cases, would result in grabbing and attracting some slag material to be flowing through this small opening to fill into the mold cavity. Right? It looks like, for example, if you're already in the airplane and for some reason the window has been broken, or there is a small opening, like the window of the airplane has been broken and it is open, right? So you will be grabbed. You're gonna find all the bodies inside the airplane will be attracted and grabbed to try to flow through or to come through this small opening, right? This is the same thing here. You're already putting a small opening and there is lots of pushing and molten metal here. So this metal will be trapped will be grabbed and will be attracted to flow through this opening. This will attract some other slag material to be filling into the mold cavity in some cases. But the non-pressurized system, it allows for the slag to fluid to enter the runner. There is no grabbing anymore, there is no attraction. It is used when the slag has the same density as the molten metal. But for this one, if the slag is high with lower density, so it's gonna be floating on the top, and we can push this one down somehow. So we won't gonna allow for the slag to come into the mold cavity. But in case that the slag is the same density, almost the same density of the molten metal, it means that it is kind of mixed with the molten metal. So it is better to use the non-pressurized system to allow for, as we mentioned, the slag to fluid to enter the runner extension. And for this gating system, the ratio of the area of the runner and the ingate both are bigger than the area of the down sprue, as we discussed before. And it is commonly used for non-ferrous metals and alloys. Make sense? All right, so what we discussed so far is the gating system and the different elements and the function of these elements. Now we're gonna demonstrate some formula that we already used in the mechanic and the sand mold design of the gating, the sand mold design in the previous meetings, which is the design of the down sprue and the boring cup. Or in other words, we are interested in finding the relation between the area of the down sprue, the blue area of the down sprue, to the top area of the down sprue. Like, keep in mind that this is like the gating system. This should be the boring cup. This is the boring cup, and this is the down sprue. This is the sprue. So as we discussed before, the sprue is tapered. So what does it mean? It means that it should have an area from the top. This is the area top of the down sprue. And it should have another area from the bottom. So this is the bottom area of the down sprue, and they should be different. So we are interested here in finding the relation between the area top and the area bottom. We demonstrated this one, or we used this relation while we did design for the sand mold. We used that the area at the bottom, this is like the bottom area, to the top area, it should equal to the area, the square root of h over hc, or this is like the hc, and this is just h, right? Which I told you, this is the boring cup, this is the boring cup height or depth. With in the sand mold design, we didn't define hc, we just defined it like h, and we said that this is the boring cup depth, and this is the cube. This is the cube height that we calculated during the flask dimensions calculation step, right? So we use this one for the down sprue calculation, especially for the area of the top to the area at the bottom of the down sprue. It was the square root of h over hc. And we said that even in the case that the boring cup depth would not given, we're gonna use this value as 50 millimeter, right? In case that it is not given. So we would like to demonstrate and prove this relation here. Starting from Euler-Bernoulli, I'm gonna give you two methods to drive this relation. The first one is based on Euler-Bernoulli, or based on Bernoulli equation that you had in the fluid mechanics, that state that h, which is just the height from any datum, plus the velocity square over 2g plus the pressure over gamma, this is gonna give us, it should be equivalent through a different section through the channel from the fluid mechanics. So for example, if we considered here this area, the bottom area, as this is like our datum, assume that, okay? So, and we would like to find this, or write Bernoulli equation at area 2 and area 3, which area 2, it should be the top area and the bottom area of the down sprue, that we're already interested in finding the relation between them. So at area 2, it should be h2, where h2, it should be the height of this area from the datum, h2 plus v2 square. V2, it should be the velocity at of this area, the velocity of the fluid, because we're already pouring a liquid metal here. Assuming that the velocity it is 0 at 1. V1 equals 0. This is the velocity of the molten metal at the tip of the boiling cup. It is 0, and then it's gonna take a smoothly flow to fill into the down sprue. And B, this is the pressure. G, this is the gravitational acceleration. This is the pressure at area 2. H3 should be the height of or the vertical location of this area from a datum, and since it is already over the datum, H3 should be 0 in this case, right? And V3, it should be the velocity of the molten metal at the area 3, or the liquid at area 3, which is area bottom, and B is still the pressure at this area. Make sense? Since we are interested in avoiding inspiration, this pressure P2, P3, both these should be equal to the atmospheric pressure, because we're just boring with the action of gravity. So we are not pushing, we are not pressuring the fluid to fill into the mold cavity, but we're just leaving it. We are filling by gravity, as we discussed before in sand mold processing. We are filling the molten metal to fill into the mold by gravity, by the effect of the gravity. So that's why the down sprue is vertical. So it means that we are not adding more pushing to the molten metal. So it means that the pressure at area 2, at area 1, at area 3, the pressure everywhere, it should be the atmospheric pressure, which is just 1 atmospheric pressure. It means that B2 equals B3. So this term can be cancelled with this term. So we're just gonna end up with this relation. As we discussed, that H3 should be 0, this term will be cancelled, so we're going to end up on the right hand side V3 square over 2G, and on the left hand side H2 plus V2 square over 2G. Make sense? Now we would like to rewrite or find a relation between the velocity of the molten metal at area 2 and area 3 in terms of the area, because again we are interested in finding the relation between, or the area of the top area of the sprue, the bottom area of the sprue, the relation in terms of the heights of the down sprue and the boiling cup, and all of these heights, HC, H2, and HT. So what we're gonna do here, we're just gonna replace V2, V3 in terms of area, and this would be through the volume flow rate. Q, this is the volume flow rate, this is the volume flow rate of the metal, of the molten metal. So Q2, this is the volume flow rate of the molten metal at area 2. Q3, it should be the volume flow rate at area 3. And since we're already having a laminar flow, so this volume flow rate, it should be constant. We are not pushing, we are not adding anything, so it should be a constant volume flow rate through the down sprue. So Q2, it means that Q2 should equal to the Q3, or in other words, as you remember from the mechanics of or the fluid mechanics class, that Q, the volume flow rate, equal the area times the velocity through this area. So the area 2 is just area 2, which we're gonna give it a name as area top, and V2, this should be the area, the velocity of the molten metal at area 2. So their multiplication gives us the volume flow rate at this area. The same thing at area 3 is gonna be area 3 over area V3. So if we divide it, for example, let us divide area 2 over area 3. So this is gonna give us the V3 divided by V2. It means that we're gonna end up with this relation. Or for example, area 3 over area 2 is gonna give us V2 over V3, which is gonna give us this relation, and we're gonna get this ratio like R, symbol R for now, right? Just R. So then if we just consider these two terms, so let us give a name to this equation like equation 2, and the previous equation here, this one like equation 1. Make sense? And this is just R. So from this relation, if you did cross multiplication, we're gonna end up with V2 equals V3 square R. Then you're gonna square both sides. So we're gonna end up with this relation. Make sense? And we're gonna give this one like equation 3. Right? Then if you're gonna look here into this figure, we defined H2, which is the height of the down sprue. Let us assume HT, this should be the total height. This total height, it should be the cube height. This should be the cube height in the step of the design of the sand mold, right? This is the total height of the cube itself, right? So H2 in terms of HT, it will be HT negative HC, where HC should be the cube. This is the boring cup height. This is the boring cup height. This is the cup height or depth. Make sense? So it means that H2 should be HT negative HC. So H2 equals HT negative HC, and this is, it's gonna be the fourth equation. Make sense? Then what we're gonna do, your objective is just to plug these things, this equation 2, equation 3, and equation 4 into this equation, right? So H2, it will be HT negative H2. So this is this first equation. This is equation 1 that we got here. If we plug this data, this information here, first of all, if we substitute for this term into this equation, we're gonna end up, this should be H2 equals, and there should be no R square here. This is just a typo here. So if we substitute V2 square equals V3 square R square into this equation, and we move this term to the right hand side, we're gonna end up with this expression, and we're gonna give a name like equation 5. This is H2 equals V3Q square over 2G times 1 negative R square. What is R square? This should be the R square relation. Make sense? Then if we substitute with H2 with this value, we're gonna end up that HT negative HC equals V3 square divided by 2G 1 negative R square. Okay, just substitute for H2 in this case. Once we end up with this relation, which it should be something here, as you can see, we can write this VHT in terms of V3. How? If you remember from the dynamic class that for constant acceleration, which is because, as we mentioned, that the fluid or the molten metal flows under the action of the gravitational force. It means that it moves under the action of G, which is the gravitational acceleration. And as you know that the gravitational acceleration is constant. So from the constant acceleration equation, with our three equations, there is one of these equations that V square equal V0 square plus 2G times H, which should be the height. So if we consider, if we are interested in V3, the velocity of the molten metal at area 3 in comparison to the velocity of the molten metal at area 1. So it means that the distance between area 1 and area 3 should be the total height. The height, it will be HT. It means that in case that this HT, this should be V1. And as we agree, V1 it is 0, as we discussed here. So what does it mean? It means that V3 square, it should equal to the 2G HT. So taking the square root, this is going to give us V3 equal the square root of 2G HT. What is HT? This should be the cube height or the total height as we discussed. And this is what gives us this equation. So if we substituted this equation number 6 into this expression here, just remove. This is a relation between HT and V3. So simply from this relation, I can say that HT, or this one, I can say that HT equals, from this relation, equals V3 square over 2G. It means that this term here equals HT. Very simple. Make sense? So if I substitute for HT here and did some manipulation to find HC, so we're gonna end up that HT negative HC over HT will be 1 negative R squared. This is gonna give us this equation. Make sense? Then we cancel out this equation. If we divide like HT over H gives 1 negative HC over HT equals 1 negative R squared. Or in other words, we can cancel this one to this one, and the negative with the negative. This is gonna give us at the end this equation that R squared equals HC over HT, or R squared negative HC over HT equals 0, or this relation. There is no need even to this equation. So it is R squared equals HC over HT, which it should be this relation here, right? So we already mentioned, so we got the R, the ratio. What is this ratio? This should be V2 over V3, which it should be the area 3 over the area 2. And this is what we need. So if we substituted, we already have r, just one r. One r, it should be the square root of h over h, right? So this r, it should be the area of the bottom to the area of the bottom of the down sprue to the area of the top of the down sprue. It should equal to r, and we got r at the square root of hc over ht, which it should be this one. So the area of the bottom of the down sprue to the area of the top of the down sprue, it should equal to the hc over ht. hc, this should be the boring cup depth, and hc, this should be the coop height, as we already, and this is the expression that we used in the sand mold design. Make sense? So this is like a proof, how we can prove this relation. Also, there is another method which is very short one. This is very long. If we decided to start from Bernoulli equation, it's gonna take lots of calculations here. But anyway, we're gonna end up with this relation. This is a second method that generally we do have. This is the boring cup, and this is the down sprue, right? As we discussed. And we do have, this is like area 1, and this is area 2, which it should be the top of the down sprue. This is the bottom area of the down sprue. And we do have, this is the total height, which it should be equivalent to the height of the coop, and in many of the cases actually. And this should be the H2, and this should be the height of the boring cup, HC. Make sense? So if I ask you to find the velocity of the molten metal at area 2 using the constant acceleration expression. The constant acceleration states that the velocity square at any point, it should equal to the velocity 0 square plus 2g times the height. So if we consider our reference here is 1 and the velocity 1 equals 0, so if this is v1, so if I ask you to find v2 square, it will be v1 square plus 2g times the height from v1, or the height of area 2 from area 1. The height of area 2 from area 1 is just hc. This one is 0, so we're gonna end up that v2, we're gonna end up with this relation that v2 equals the square root of 2gh. How about v3 square? It's gonna be v1 square plus 2ght. This one is 0. So taking the square root, this is gonna give us this expression for v3 as well. Like v3 is gonna be the square root of 2gt. Why ht? Why ht? Because we are already finding the velocity of at the area 3 in comparison to the velocity at area 1. So I have to consider the height between them, which is ht. But hc I considered before because this is the velocity at area 2 in comparison to the area 1. So the height between them was hc. Make sense? So we got these two relations. In addition, if I ask you to, so simply, if we divided these two expressions together, like v2 over v3, this is gonna give us the square root of 2g hc over 2g ht, right? And the 2g will be cancelled with the 2g. This is gonna give us the square root of hc over ht. Now we have to define the velocity ratio in terms of the area ratio using the volume flow rate. That the volume flow rate at area 2 should equal to the volume flow rate at area 3. So q2 equals q3. This is gonna give us the area 2 v2 equals area 3 v3. If you divide area 3 over area 2, this should give us v2 over v3. So then plug this relation here, you're gonna end up that the area A3 over area A2, which it should be the area of the bottom to the area at the top of the down sprue, which is equal to the square root of h over h, which is hc over ht, as we discussed. So this is another way, which is a short method to find the components, to find the relation or the area of the bottom sprue to the area of the top, the top area of the down sprue as a ratio of the heights of the boring cup and the height of the coop of the sand mold. Make sense? So this is for the gearing system and the different element that we discussed. The next that we're gonna move to is the buoyancy force. Okay, so I'm gonna discuss this buoyancy force very quick. And in the next meeting, we're gonna discuss the design of the riser. Then I'm gonna give you, in another video, in a third video, we're gonna discuss, I'm gonna solve some examples on the design based on the buoyancy force, the design of the riser in addition to the design of the down sprue. It means that these relations that we demonstrated here, we're gonna consider them in some problems as well, okay? And this is gonna be covered through exercise 4. So for the buoyancy force, as we discussed before, it is a big deal. It is a serious problem that, or one of the things that we have to take precautions while we do design for the sand mold. One of the hazard, it is one of the hazard during the boring process of the molten metal is that the buoyancy of the molten metal may displace the core or left the cube itself. We probably have a cube, especially in case that a core of a molten metal, and we said that the core we're gonna use it to form interiors or any internal openings in the casting. In case that they would have this core is located horizontal in the sand mold, so the buoyancy force will be a big deal, and it will start to push the core. In addition, it would lift the cube of the drag and will result in some displacing in the cube with respect to the drag, and this definitely will result in some defects in the product. So we have to avoid this buoyancy force, or to take precautions to minimize the effect of this. Not minimize, because anyway this buoyancy force will be there, but we have to keep the cube and the drag stick together against the buoyancy force. So the cube is prevented from being lifted by clamping it to the drag, one of the ways, or by placing weights on the cube. As we said that, even if you remember that we said that this is the cube and this should be here, the drag, and this should be the cube. And in many of the cases, and this is the flask, and there should be mold cavity and the gearing system and the riser, these other things of the sand mold. So in many of the cases, we could use these handles and add here some bolts and nuts to clamp these two parts together against the buoyancy force. The buoyancy force is some pushing that comes from the molten metal acting on the cube to push this one, so it will shift the cube with respect to the drag. The cube will move right and the drag would move left, so this will result in some defects in the product. So we have to avoid this one. We have to prevent lifting the drag with respect the cube with respect to the drag by clamping them together, or in other words, we would add some weights on the top of the cube. So we would add some weights here. Okay. So the buoyancy force is the force that the molten metal exerts on the cube at this surface. Like there is some pushing, as we mentioned before, like this buoyancy force is gonna keep pushing the cube, so we have to avoid this buoyancy force. The objective is to calculate the weight here in this part, is to calculate the weight needed to overcome the buoyancy force of the molten metal. How much of weight that should be added to avoid the buoyancy force. So to do so, basically, you're just gonna consider like solve a simple problem of the kinematics that we considered before. Like first of all, there is a buoyancy force, which is the pushing over the cube. This buoyancy force can be calculated using this simple relation that if m where, or just F, just a force, this is the buoyancy force, like this is the force come from the metal, this is the M stands for the molten metal force. It should be the density of the, this is the density of the molten metal, like the density of the steel, it is 7.8 grams per centimeter cube, and G, this is the gravitational acceleration. In addition to H, this should be the height of liquid metal level up to the down sprue. And in many of the cases, this is the height of liquid metal level up to the sprue well, up to the sprue well. In many of the cases, this H, it will be equal to the HC, which it should be the cube height. So it's gonna be considered as the cube height in many of the cases. And in some other more complex designs of the sand mold, this H, it shouldn't be the HC, but we won't gonna consider these complex things So we're gonna consider the cases or all the design calculations or the design problem of the sand mold that we considered are simple, and we already considering that in this h for this problem, h will equal to the cube height. This area should be the projected area of the mold cavity. So what does it mean, the projected area? If the mold cavity, for example, is a rectangular shape, this mold cavity, this is the cavity inside the sand. If it is a rectangular shape and it is gonna be casted horizontally, it means that the projected area, it will be the top area. If I ask you to look at it from the top, you're gonna see this area. This area, it will be the projected area, which we're gonna use it as A in this equation. But how about, for example, if we do have the casting is cylindrical shape and it's gonna be casted vertically, it's gonna be casted in the vertical direction, so the projected area will be this one, because if I ask you to look at it from the top, you're just gonna see this circular area, so this area will be the projected area. But how about if you do have the same casting, this cylindrical one, but it will be casted horizontally. So it will be located in the sand in the horizontal direction. It will be located horizontally. So if I ask you to look at it from the top, you're just gonna see this cylindrical surface, but this cylindrical surface will be projected over rectangular area. The projection, if I ask you to draw a projection of this cylinder, it will be represented as a rectangular area. So this will be the projected area. This is the projected area. In case that you do have the cylinder, it will be casted horizontally. And we're gonna discuss this with more detail, especially when we consider examples over this method. But anyway, this is the equation or the formula that we're gonna use for the buoyancy force calculation. It is basically, we drive this one, it is the conventional buoyancy force of the fluid mechanics. It is the rho, the density of the molten metal, times G times H times the area, where this area and the H, they are kind of related together to the weight of the, because if you remember from the fluid mechanics that this buoyancy force, it is related to the amount of molten metal displaced because of liquid displaced because of the volume or the weight of the mass, the weight of the object, the solid object already floating or merging into the submerged into the liquid. So this buoyancy force relation, it depends on rho G H A, where rho, this is the density of the molten metal again, and G, this is the gravitational acceleration. H, it should be the height of the cube height, and H stands for the projected area of the mold cavity. And this projected area of the mold cavity depends on how we are going to cast the product into, it's gonna be the shape, depending on the shape of the product. In addition, how it's going to be casted vertically or horizontally, and this will be much more clear when we consider example over this formula. So if we already have been asked to calculate the weight needed to be added on the top of the cube to avoid or to prevent the displacement or lifting the cube with respect to the drag because of the buoyancy force, as I mentioned, we have to do some calculations in terms of the mechanics of the model. Like for example, we do have some pushing, we do have one force which is Fm. Assume that we do have a particle here, and we do have one force that this is the buoyancy force pushing up, and this particle, it should have some weight. This weight it should be, so this buoyancy force is already acting over the cube, and the cube itself, it has a weight. So if the buoyancy force, it is not bigger than the weight of the cube, so there is no need for adding more weights on the top of the cube, right? Because the cube is heavier, is more weight than the buoyancy force. It can overcome the buoyancy force by itself, or the buoyancy force, it is not big to push or move the cube because the weight of the cube is huge. So, but in case that the weight of the buoyancy force is bigger than the weight, in case that Fm is bigger than the weight of the cube, this is the weight of the cube. So in this case, more weight is needed, more weight is needed. Make sense? But in case that the weight of the cube is bigger than the buoyancy force, so there is no more weight is needed. So how about how we can calculate the additional weight? Definitely it will be the difference between the weight of the cube and the buoyancy force that already there. Make sense? In case that we have a core and the core is located horizontally in the mold cavity, the pushing, it is not just over the cube, but it will be over the core, and the core will keep pushing over the cube. It means that there will be another pushing, but through the cube, right? Through the core. So for example, in case that you have a core that is located horizontally inside the mold cavity, these are the core branches, and assume that this is the like a hollow cylinder in this way, and the thing in the middle here is the core. So there should be metal. This is molten metal. This molten metal is gonna keep pushing over the core itself, and since the core is already fixed in the sand, like assume that there is here, this is the cube. All of this is just sand, and this is the cube part, and this is the drag. And all of this metal, this is the drag. So there is bushing, and this bushing is already acting over the core, and the core itself is gonna keep pushing over the cube, right? So there is a pushing, there is a buoyancy force, or there is a pushing force, but through the core. In addition, there is definitely pushing force through the cube itself, over directly. Like the molten metal on the top here is gonna keep pushing the cube. In addition, there is another pushing of the molten metal over the core, and then the core is gonna keep pushing the cube. It means that we do have like two different buoyancy forces already, but one is a direct one come from the molten metal directly acting on the cube. The second one is indirect one through the core, right? So how we can calculate the total buoyancy force? This total buoyancy force, it will be FB, which is the buoyancy force that comes through the core. This is the force through the core. You could consider that this is like indirect force, and this is the direct buoyancy force. This is the direct buoyancy force from the molten metal to the cube directly. Make sense? And the buoyancy force acting over the core, it should equal to the weight of the molten metal displaced by the core negative the weight of the core. This is from the Archimedes law, from the fluid mechanics. Okay, like the buoyancy force over the core, like assume, because the core in this case it is a solid object that is totally submerged or located or floating into a liquid, surrounded by liquid from everywhere, right? So it should be the buoyancy force acting over the core, it should be the weight of the molten metal displaced by the core negative the weight of the core itself. Make sense? So simply the core is gonna displace metal by its volume, equivalent to its volume, and its weight can be depends on the volume of the core itself. So we can easily end up with a very simple relation here, like this FB directly, it can be written as the density of the molten metal negative the density of the core times the volume times G. What is the volume? This should be the volume of the core times G, which is the gravitational acceleration, to end up with the force of a weight, right? Because the volume of the core is gonna remove metal by its equivalent to its volume, and G the gravitational acceleration. So simply we're gonna subtract the difference between the weight will be the difference between the density rho. This should be the density of molten metal, while the rho C, it will be the density of the core. And remember that the core is made of sand, so it should be the density of the sand anyway, which it will be given. And VC, it should be the volume of the core. Make sense? So in case that we have a core that is located horizontal into the mold, into the sand mold, definitely we have to consider another pushing comes from the core itself, and the total force will depend, it will have like two components, one is direct, one is indirect through the core, and this is what we're going to discuss when we consider examples with more detail through the next meeting. Okay, so these are some examples, you're going to find them through these slides, but anyway, these examples we're going to consider them with more details on the buoyancy force, also the calculation of the area of the down sprue or the top or the bottom sprue. It means that these formula that we already discussed here through this lecture, we're gonna discuss them with more detail through more solved examples. The next meeting, we're gonna discuss the design of the riser. Then we're gonna consider if there is some time that we can or in a separate video I'm gonna discuss the design of the riser. Then in a third video I'm gonna solve some examples on the riser design, the buoyancy force, and the calculation of the down sprue. So there are three types of problems here: riser design and the buoyancy force calculation, in addition to the calculation of the area of the top of the top area of the down sprue to the bottom area of the down sprue. Make sense? So that's it for today, and again the next meeting will be on discussion on the riser, and thank you, and see you in another video.